All right, in this podcast, we're going to talk a little bit about nuclear chemistry. Nuclear chemistry basically is the chemistry of the nucleus. So we're talking about protons and neutrons here, the nucleus. When atomic nuclei are unstable, it's usually because they have the wrong proton to neutron ratio, okay? So there's just not, it's not a good balance, okay? So there's either too many neutrons or too few protons, okay? These unstable nuclei undergo radioactive decay in an attempt to become stable. So radioactive decay is going to allow them to alter the number of protons or neutrons, and in this process they basically give off radiation to gain stability. So they're going to alter these protons and neutrons by giving off some radioactive particles. There are three types of radioactive particles that are often given off in an attempt to gain stability. The first is alpha, then beta, and then gamma rays. So these are not the only ones, they're just the common ones. All right, so here's a little chart that kind of summarizes the three particles. Alpha have the symbol, this little A looking thing to the side, and 2, 4 being the mass, 2 being the protons. Okay, so we know that it has a 2+ charge because there are no electrons. Okay, this is all that's given off is 2 protons, 2 neutrons. It's also the same as a helium nucleus. Okay, so basically sometimes you'll see the alpha symbol, sometimes you'll see the helium symbol. Beta is 0, -1, so it has a mass of 0 but -1 charge. So basically that makes it an electron. Okay, so beta is like an electron. And then gamma is 0, 0, no mass, no charge, and this is a little funky Y. Okay, now they have different penetrating power. So basically it's talking about how far they can go into a substance. Alpha has very low power, beta has medium, and gamma has high power. And then we see that alpha can make it through paper and clothing. Okay, so you can hold up a piece of paper or some clothing and that will protect you from alpha particles. If you want to be protected from beta particles, you will need some sort of metal foil, be it aluminum foil, gold foil, some sort of a metal foil. And then gamma, you need either lead or concrete to shield from those. Here's a schematic that's showing that alpha can be shielded by your hand, beta must be stopped by some sort of metal, gamma ray, you're going to need either lead or concrete, and then neutrons, which we didn't really talk about being ejected, you can see they can go much further. All right, so let's think about this. If an atom gives off one or more of these particles to become stable, well, what happens if it gives off an alpha particle? An alpha particle is 2 protons and 2 neutrons. Is it going to be a different element now? Well, yes, it's going to be a different element. If you change the number of protons, you've changed the element. Okay? So yes, that's the whole idea, is that the unstable nucleus gives off a proton or neutron or some combination thereof through these particles, and then the nucleus of the element changes, or the atom changes, and that can result in a different proton number, which would change the identity of the element. All right, so let's talk a little more about alpha emission. So remember that alpha is the same as a helium nucleus. Here's an example of a uranium-92 atom giving off an alpha particle and becoming thorium. Okay, so all of these equations are written as decay equations. Okay, they're decomposition equations. Note that the mass lost 4 here and the atomic number lost 2. Alpha emission is most common in large nuclei, so we're talking atomic number 60 and up. Beta emission, however, is when you give off a particle that's just like an electron. So basically, when beta decay happens, the nucleus takes a neutron and changes it into a proton and an electron, and then it emits the electron. Okay, so basically the mass number doesn't change because you're trading a neutron for a proton. They have the same mass, but the identity of the element does because it gains a proton. Here you see a carbon atom emitting a beta particle and becoming a nitrogen atom. Notice again, mass numbers stay the same, atomic numbers go up by 1. So we're going to expect beta decay if the isotope's mass number is bigger than it should be. So here we have carbon 14. We know that carbon's most stable around 12. Okay, so it has too much mass, which means it has too many neutrons. So we're going to try to change those neutrons into a proton. Now, gamma rays are the last thing that are given off. They are very dangerous electromagnetic radiation waves. They have no mass, and they're usually emitted with other types of radiation. So you're going to see a gamma particle either paired up with an alpha or a beta. Now, how do we solve transmutation equations? Well, it's not that difficult. This is a transmutation equation. It's basically two separate mathematical equations. So you think about the top numbers separately, then you think about the bottom numbers. Make the arrow your equal sign. So the top would be 238 equals 4 plus 234. The bottom would be 92 equals 2 plus 90. Now if you took out one of these, maybe took out the thorium and we're trying to find that, then you could make variables and solve for the missing number. So 238 equals 4 plus x. So you would know that you would subtract 4 from 238 and you get 234. Okay? All right, transmutation is the conversion of one atom to another. So those are the equations you just saw. A transuranium element is any that has an atomic number above 92. So transuranium, past uranium. And all these elements are man-made. Fission, which is what we're talking about right now, transmutation, is the splitting of a nucleus into smaller fragments, okay? You can cause this to happen by bombarding a nucleus with neutrons. This is what happens in nuclear bombs and nuclear power. It's a chain reaction, has high energy, and you can use control rods, which are inert substances that are not affected by neutrons that will slow your reaction down. Fusion, we haven't talked about yet, but it's the opposite of fission. So it's when you take two nuclei and you combine them to try to produce a bigger nucleus. It produces lots of energy. It's too hot to control, very, very hot process, and the sun does it every day. So how can you make an element in a lab? Well, fusion is one way. Why are elements larger than 92 not stable? Because the nucleus becomes too big to remain stable for too long, okay? So once you get that big, the protons are pushing away from each other, and that strong nuclear force is not enough to hold the whole nucleus together anymore. All right, last topic is half-life. Half-life is the amount of time it takes for half of a radioactive substance to decay. Half-life is used in radioactive dating, which tells us how old something is, and in medical procedures to diagnose and treat disease, or trace a particle through your system, such as a DNA or a fertilizer or something like that. When you solve a half-life problem, you're going to create a table. The table should always have time and your sample, okay, or percentage, whichever you want to label it. Time always starts at 0, sample always starts at 100%. Now, every time a half-life goes by, we lose 50% of the sample, okay? So from on the time side, you're just adding a half-life every time, okay? Now on the percentage side, the percentage is cutting in half every time. Okay, so we should use this to solve this problem. Okay, so we know that carbon 14 undergoes beta emission to turn into nitrogen 14. The half-life is 5,730 years. Only 12.5% of the carbon 14 is left in a bone found in a dig. How old is it? So you should make a chart. The chart's going to have time on this side, percentage on this side. Time starts at 0, percentage starts at 100. Every time the percentage cuts in half. And you add a half-life every time. Okay, so pause your video and try it yourself real quick. Then come back and check your answer. All right, hopefully you're back from trying to do this problem yourself, and hopefully you got this, okay? So your sample cuts in half every time. Okay, so it has to be cut in half once, twice, 3 times, and then you're adding a half-life every time. So after 3 half-lives, it's 17,190 years, so about 17,000 years old.